right, hopefully you can see performance portability of the Chapel language on diverse architectures.
Yeah.
Great. So my affiliation for this was listed as Australian National University. I actually work at Oak Ridge National Lab, but this is work that I did with a couple of students, undergraduate students at ANU in Canberra. All right. So this first graphic is something I stole from Engen. Thank you, Engen. Just demonstrating how we've now got the ability in Chapel to compile a single Chapel source code for running on multiple targets. And so right now, the important targets that I'm interested in are CPUs, but obviously also the GPUs, the NVIDIA and AMD GPUs through LLVMs, PTX, and GCN backends. So this is a great situation to be in where we have a single code with potentially multiple backends. But what we're interested in is the question of performance portability. So what is performance portability? It's two concepts intertwined. The first is that you can write an application code and it will run correctly on many different hardware platforms without having to rewrite it each time. And also that each of those hardware platforms achieves acceptable performance by some metric, again, without having to do platform-specific optimizations. And the reason we care so much about this is, the national labs and other big organizations spend literally years of time personal years of time every year rewriting or optimizing codes for the latest new architecture. And we'd like to minimize that effort where possible. So in characterizing performance portability, we're going to use a metric that is due to Pennycook and Sewell and Lee, this double P metric, which is essentially the harmonic mean of efficiency on each platform. What is efficiency? You can measure it in two different ways. One is called architectural efficiency. You can take a figure like, say, the vendor's reported peak flops for the platform, how many teraflops they think their GPU should get, and then you can measure what fraction of the peak flops you actually achieved on your application. And the other way to measure things, if you don't have a particular figure of merit that, other than the runtime, you can just take the runtime of the application and call the fastest version 1, and then every other version of the application, you take the inverse speed up. So, every version is going to be slower than the fastest. Importantly, if your code does not run correctly on every platform, the double P performance portability metric is 0. So you get a straight up fail if you fail to run on any platform. So the question we wanted to look at was, how well does Chapel compare to more widely used programming models like OpenMP and Cocos in this metric of performance portability? So what we did was create new Chapel versions of 3 mini applications. These are all coming from the University of Bristol's High Performance Computing Group, who've done a lot of surveys of performance portability. And they've already got really good implementations in OpenMP, Cocos, CUDA, HIP, SQL, and a bunch of other programming models. So the apps we looked at are Babelstream, Minibude, and Tleaf, and they all have different properties, patterns of computation that they use. We didn't look in this study at multi-device GPU codes. We didn't look at distributed memory, multi-locale across a cluster codes. And we didn't look too much at programmer productivity, but I will make a couple of comments about productivity as we go along. All right, so the first app was Babelstream. So Babelstream is just a stream code. Essentially what you're doing here, you're taking 2 or 3 vectors. So these A, B, C things are vectors of floating point elements. You're iterating through them and performing some operation on the matching elements in each vector. So essentially we're performing vector copies or additions or multiplications by a constant, that sort of thing. Where each of these have a different balance in terms of the numbers of loads and stores from memory versus the number of floating point operations that they perform for each element of a vector. We're going to look at the performance results from the Babelstream triad, which is essentially scaling a vector by a constant, adding it to another vector, and then storing the result in a third vector. And if you want to see the code for this, it's here on GitHub, and that will be in the slides, which we'll share later. Okay, so how does it look implemented in our different programming models? We'll look at Chapel first of all. The Chapel implementation is really nice and simple. You might not be surprised. We use the for all data parallel loop and we iterate over each of the vectors. We could have even done this probably slightly more simply by just writing A equals B plus scalar times C. Chapel has array lifting, but this is how we implemented our triad. And I've also shown you here how we allocate the memory in a way that's portable across both CPUs and GPUs. We decide at the beginning of we choose a stream locale at the beginning of the program, and we allocate our vectors on that stream locale. So for the CPU code, when you compile this for a CPU, it's going to be decomposed into chunks and spread across worker threads on the CPU. When you compile it for a GPU, it's going to be compiled to a kernel, either in PTX or GCN, depending on which flavor of GPU you're using. And each thread is going to operate on one matching triad of elements. And of course, Chapel also generates the host side code for kernel launch synchronization. So that's really all there is to triad in Chapel. Okay, in CUDA, it's a little bit more complicated. Yes, you have to write the kernel, similar to how we've done in Chapel. You also have to write some code to launch the kernel and then synchronize with the kernel. So there's a few more lines of code in CUDA. COCOS, it's a little bit more complicated again. COCOS operates on memory with this concept, of views. The COCOS code is probably about as simple as it could get. COCOS has parallel loops. You can see here the parallel for data parallel loop, very similar to Chapel's concept, but we do need an explicit synchronization in COCOS. Okay, so you might not be, an OpenMP, a little bit more complicated still, and you might notice already creeping in here with OpenMP. Unfortunately for the developers of this benchmark, it wasn't possible to write a single version for OpenMP that performed equally well on CPU and GPU, and we found that with a number of the benchmarks. So already you don't really have a single source here. Okay, so we wrote this code. We ran it across a really wide range of platforms. We've got Intel CPUs, AMD CPUs, an ARM CPU, and IBM Power 9. Also NVIDIA and AMD GPUs from multiple different generations. And they've all got different capabilities in terms of compute and memory bandwidth. But we wanted to see how performance portable we are across multiple generations and multiple vendors. Okay, so you might not be surprised to find out that the performance of Babel Stream is pretty good for all the programming models across all of the platforms. It's very similar. It's a very simple benchmark, so there's not much to separate between Chapel, OpenMP, COCOS, CUDA, and HIP. You'll notice we've summarized these results down the bottom by giving this double P metric of pennycook. And you'll notice that CUDA and HIP are given 0 for all platforms, and for CPUs, that's because, of course, they're not designed to run on some of the CPU platforms. And unsurprisingly, the best performance for the stream benchmark comes from the platform, the A100 GPU that has the highest memory bandwidth. That's the best raw performance. But we can look at the architectural efficiency for different platforms, and you will notice that the NVIDIA GPUs do tend to achieve a higher proportion of their vendor specified bandwidth than, say, some of the CPU platforms. Okay, so Stream is really simple. Let's look at a slightly more complicated app. This is MiniBude. MiniBude is a proxy app for a protein simulation. We're computing energy using a molecular dynamics simulation over pairs of proteins and ligands which come together in different poses. And so you will operate over a very large number of poses and try and find the lowest energy. So this is really arithmetically intensive. It will perform well on any platform that has good floating point capabilities. The core of this benchmark is a triply nested loop over proteins and ligands and poses, and in all of the implementations, that's further decomposed with a fourth nested loop where we divide those poses into a number of poses per work item, PPWI. So this is the Chapel loop code. We use a single data parallel loop at the top level, and then we use a vectorized 4-param loop in the middle. And that's really the same as the CUDA code. We followed the parallelization there. We now need to transfer data to the GPU, and in Chapel, again, that's really simple. We're doing this through array copies mostly. So we're just doing a direct array assignment to a GPU variable, or in some cases, we're doing an assignment to a slice of an array on the GPU. Okay, so when we look at the performance of miniviewed, it's much more variable both across platforms, but also across programming models. So there are a few interesting results here, which I'll call out. First of all, I guess in terms of raw performance, the best by far was the Intel Sapphire Rapids CPU. This has an enormous number of cores and very high floating point capability for a CPU. It costs about as much as a GPU as well. But in terms of architectural efficiency, the story was very mixed. And what we'll notice, first of all, is that overall, Cocos does really well if you look across all of the platforms, but there are some standout bad results, particularly on Power 9. Both Cocos and OpenMP performed appallingly, and you'll notice when computing this performance portability metric, I've actually removed Power 9 because for harmonic mean, such a low result really skews it versus all of the other platforms. So this is the result excluding Power 9. Pardon me. Good news for Chapel. If you look at the GPU results, so we're looking across all of these NVIDIA and AMD GPUs, Chapel performed best across the GPU platforms of any of the portable programming models. So it significantly outperformed both OpenMP, libopenMP Target, and Cocos across the GPU platforms. It also performed reasonably well on CPUs. And I guess an important thing to note about the miniviewed implementation, this was written by an undergraduate student at ANU in a semester. He was actually able to complete not just a single GPU, but a multi-GPU implementation of this. So Chapel miniviewed, this code would run correctly on as many GPUs as you have on your node. You can't say that about the other programming models. They're all single GPU implementations. Okay. Right, the final proxy app is tleaf. So tleaf is a stencil solver. It's a sparse linear solver over a 2D grid. The arithmetic intensity on tleaf is a lot lower, so you would expect it to perform better on those platforms that have a better stream balance. They have a higher memory bandwidth versus their floating point capabilities. The indexing in tleaf of the data is very interesting. We're operating over 2D index domains, and so ideally we'd like to expose the parallelism in both dimensions in our parallel loops. So in OpenMP, that's done through, in the OpenMP target implementation, we're distributing the loop and collapsing it across both nested loops here over J and K, the 2 dimensions of the domain. In Cocos, that's done slightly differently. Cocos collapses, like the programmers collapsed those 2 loop indices into a single dimension and then distributed that. And then you can see the Chapel code here. It's a one-liner. So we have 2-dimensional Chapel domains, and we can just iterate across them and perform the operation. Again, all of these codes are available on GitHub. tleaf has a huge use of reductions, and in Chapel 2.0 at least, unfortunately, GPU reductions have to be computed in global memory. I know that there is work underway, and I think it's hit the main branch already of Chapel to allow reduction intents to be used for GPUs in Chapel 2.1. So right now, this is what the Chapel reduction code looks like, and that's what we measured, but it'll look different for the next version. Chapel's indexing, we found, really made the Chapel code much more readable than some of the other programming models. It performed really well on the CPU platforms, and I know a lot of optimization's gone into that. However, we did find some problems with 2D domains on GPUs. And the reason why is for a 2D domain, the first dimension will be assigned to the GPU threads, and any remaining dimensions will be implemented as loops inside of the kernel. And so you can imagine that reduces the available parallelism for your GPUs, so you don't get full, utilization of your GPU. And so what we did, we actually compared 2 different Chapel versions, one using the 2D loop that I showed you before, and one using a sort of a hand-optimized 1-dimensional loop. So this is similar to what Cocos was doing, collapsing the loops by hand. You'll notice it's a lot simpler than the Cocos version, but it's effectively the same thing. Okay, so the results. T-Leaf, as I mentioned, Chapel's performance on T-Leaf on the CPUs was really good. In fact, it was significantly the best performance of all of the programming models on CPUs. Unfortunately, you can see down the bottom here the performance on the GPU platforms. First of all, looking at the 2D loops, you'll see the effect of what I mentioned, the lack of utilization of occupancy on the GPU really killed Chapel's performance there. When we converted it to a one-dimensional loop version, performance improved a lot on the AMD GPUs. We're still seeing a bunch of problems on the NVIDIA GPUs, and we believe these to be largely due to how Chapel passes parameters relating to the index domains. So a bit of a mixed result for Chapel there. It was also a mixed result for the other programming models. You can see OpenMP also didn't necessarily achieve the best performance on GPUs, even with its two different versions. Overall, OpenMP did achieve the highest performance when you take into account the CPU platforms as well. And maybe unsurprisingly, the native programming models, CUDA and HIP, achieved good performance on their respective platforms. Okay, so in conclusion, we found it really useful using this double P metric of performance portability as a way of looking at the portability of different models and identifying areas of strengths and weaknesses by breaking it down into different subsets of platforms, CPUs and GPUs, like we did. Since the last time that the University of Bristol group have presented performance portability results, we've noticed a significant improvement in both OpenMP and CoCos. So that's been, the compiler writers have really been working hard on those implementations, which is great. But we also found that Chapel really compares favorably to both of those models if you want to do performance portable programming. Some really nice things about Chapel: the code is much shorter, sometimes half as long as the other versions. It mostly gets good performance, modulo some of the things that I mentioned earlier. And as I mentioned I should have also mentioned for T-Leaf, that was actually a multi-node code. So again, all of the other models were a single device, single node. The T-Leaf was multi-node, and you saw the performance just running on a single device there. So it makes transition to scaling up much easier. There are still some issues with the Chapel GPU code generation, and we're hoping these will be fixed. So I'll stop there. Just thank everyone who assisted with this work.
Thank you, Josh. Are there any questions? If so, please feel free to unmute yourself. If not, I'll start. I was wondering, could you comment on your experience, like how complicated it was to handle kind of CPU and GPU arrays transparently in Chapel? How much branching does it involve?
Right. So yeah, I did show right at the beginning. The example for Babel stream is probably the simplest one. Sometimes you can get away with this kind of branching code. You decide which locale you're running on ahead of time, and then using a Chapel on statement to move to that locale for both allocation and computation. What I didn't show you for Minibud was we did have some more complications there. For example, we found with Minibud the performance of for each versus for all was different in CPUs versus GPUs. Yeah, again, this is something we've been talking with Engin about, whether that can be the performance can be unified. So right now in Minibud, we actually do have a branch there that chooses one or the other, depending on if you're on a CPU or GPU. But largely, almost all of the code, like almost every line of code in Chapel is single source, apart from those kinds of branches of where are you going to allocate the data and that particular performance gotcha for all versus for each. And of course, for T-Leaf, this one-dimensional versus two-dimensional thing right now. Yeah.
Thanks.